not my first visit to Japan, but the first visit to the city of Hiroshima. And of course, I would like to thank Professor Smaluch for his invitation to take part in this school and to give this talk. Actually, the talk will consist of two parts. Essentially, it will be two parts of the same very general topic. You can see the name of this topic here, multidimensional solitons. And because the structure is organized so that the first talk should be a tutorial, and the second should be at the level of a research talk. So I will try today, in the course of this hour, to present some relatively simple elements of this topic. And then next week, it will be Tuesday maybe, there will be the second part where I will try to present some more sophisticated parts, which can be considered already as elements of ongoing research in this field. Okay. So the title is Multidimensional Solitons, and I will try, of course, to explain what it means. So first of all, about solitons in general. Probably most people in this room, and also those who join through Zoom, they have some, at least general idea of what solitons are. So solitons are solitary waves. These are stable, localized objects which exist in a great variety of physical media. And this stable shape, localization, is a result of the balance between two different types of factors. On the one hand, the system, of course, includes linear properties, such as typically dispersion or diffraction. And these are classical effects which try to stretch any localized pulse. If you can create the localized pulse as an input, as an initial condition, and then these linear effects will try to broaden it. On the other hand, if simultaneously the effect of the nonlinearity in the medium is sufficiently strong so that it can compete with the linear effects, in that case, it depends on the sign of the nonlinearity. And if the sign of the nonlinearity is what is called, in optics, is called self-focusing, or in other realizations, it's called self-attracting, so that, roughly speaking, different elements of the wave field attract each other. And they, naturally, due to the self-attraction, they try to make this pulse very narrow. Then, in very many cases, the system is able to maintain the stable equilibrium balance between this linear effect, which tries to stretch the localized state, and the nonlinear effect, which tries to compress it. And so this gives rise to the stable localized pattern. Solitary wave, or the most commonly adopted name for it is a soliton. Okay. So probably, arguably, the most famous equation which gives rise to solitons is the equation that probably is known to many of you. It is written here. It is called the nonlinear Schrödinger equation. It's written in the one-dimensional form, so it's a partial differential equation, which for the complex function psi, which is a function of time. This is an evolutional variable and coordinate x. And so this term represents the, depending on the physical interpretation, it may be called either diffraction or dispersion. And then we have the nonlinear term here. What is essential? The signs in front of these terms must be the same. In that case, actually, when the signs are identical, both minus or both plus, in that case, this is indeed the situation when effectively the nonlinearity, this cubic term, has a self-focusing or self-attractive sign, and then it is able to maintain the stable balance with this linear term, and as a result of the balance between them, this equation gives rise to these famous elementary solutions, which is written here. So these are famous solitons. It's a very simple solution, which can be found by an undergraduate student. Just if the student would like to find a simple analytical solution of this equation in the form of the traveling wave. So traveling wave, because we have this argument x minus ct, so this means that c may be the arbitrary velocity of the soliton. In particular, of course, it may be 0. And then the second non-trivial parameter is this parameter eta. Eta has simultaneously two manifestations. On the one hand, it determines the amplitude of the soliton, its largest value. On this other hand, because it appears in as a factor in the argument of hyperbolic cosine, obviously, it simultaneously determines the inverse width of the soliton. So roughly speaking, the width of this localized function is 1 divided by eta. And then there is also this frequency, which is a part of the solution. Okay. In terms of the mathematical analysis of this equation, it has an extremely fascinating property, which is called exact integrability. Actually, there are two different nonlinear Schrödinger equations with different signs in front of the cubic term. First, now in the context of this talk, we are interested in, as I already mentioned it, in the case when the sign there is a bottom sign minus, because then the nonlinearity is self-focusing. On the other hand, one can also write the equation with the opposite sign plus. In that case, effectively speaking, the nonlinearity will be self-defocusing. Both, of course, these equations are not equivalent to each other, definitely. One equation cannot be transformed into the other, and they give rise to completely different solutions. Both of them have many real physical implementations, and both of them share this fascinating property of the exact integrability. So for both these equations together, the fact that they are integrable equations was discovered back in 1971 in a classical work by two authors in the former Soviet Union very long ago, Vladimir Zakharov and Alexei Shabat. Zakharov was an extremely famous researcher in a very broad field of nonlinear sciences. Unfortunately, he died just a few months ago. He was, I guess, 85 years old. Okay, so this classical work was published in 1972. Actually, 1997 is the original version in Russian was published in 1971, and this in 1972. This is a publication of its English translation. Okay, so they demonstrated by means of quite a sophisticated mathematical technique, which is called, for some historical reasons actually, which is called inverse scattering transform. And it was the technique itself, in principle, was discovered 4 years before their work. In the when the very first integrable equation was discovered, it's the famous Korteweg-de Vries equation. Its integrability was discovered in 1967 by the group of, in the United States, by the group of mathematicians whose leader was also a very famous applied mathematician, Martin Kraskell, who also unfortunately died. And so they, in principle, discovered this remarkable mathematical technique. And then in this classical work, Zakharov and Shabat applied these ideas, but in a much more sophisticated form in order to demonstrate the integrability of both nonlinear Schrödinger equations with both signs in front of the nonlinearity. So, first of all, as concerns the physical implementation of the solitons, originally solitons were discovered, as a matter of fact, in this first classical paper by Zakharov and Shabbat. It's a very simple elementary solution, as I mentioned. An undergraduate student can easily find it if the student is given this as a home exercise. But nevertheless, this elementary solution, together with a huge number of much more sophisticated solutions, was found by Zakharov and Shabbat in 1971. And then soon after that, 1973, there appeared another famous theoretical paper by Hasegawa and Tappert. Hasegawa is a very famous Japanese scientist. And what they did, they actually derived exactly the same nonlinear Schrödinger equation in terms of fiber optics. So they started from the full systems of the Maxwell's equations for the propagation of light in an optical fiber, and they took into regard the classical effect, which is called the Kerr effect. Kerr effect means that the effective refractive index of the dielectric material has correction to its so to say, to its material value. There is an effective correction which is proportional to the intensity of the propagating light. So it was discovered experimentally by the British physicist Kerr in the 19th century. So, and Hasegawa and Tappert, they analyzed the systems of Maxwell's equations for the propagation of light in the material medium, in the optical fiber. And they were able, by means of a large number of simplifications and approximations, which were physically relevant, they were able to demonstrate that effectively one can derive exactly the same nonlinear Schrödinger equation as was in a purely mathematical form discovered by Zakharov and Shabbat. And therefore, because the existence of solitons was already known from Zakharov and Shabbat, Hasegawa and Tappert, they predicted that solitons may exist as a real physical object in an optical fiber. So this idea was picked up by experimentalists, by this group of very famous experimentalists working in fiber optics, Mollenauer, Stolin, and Gordon. And 7 years after this prediction was made by Hasegawa and Tappert, these people had published the work where they reported the experimental observation of the soliton in the optical fiber, or solitons is better to say, solitons in the optical fibers, as it were exactly in the same shape as was predicted by Hasegawa and Tappert. So this is an image taken from this classical experimental paper by Mollenauer, Stolin, and Gordon. So what they observed first, they launched into the fiber a relatively weak signal. Relatively weak, this means that the nonlinearity is not a significant factor. So, well, this was actually, in the case of the optical fiber, the evolutional variable is not time. It is a propagation distance along the fiber, and the effective coordinate is actually a linear combination of the physical time and propagation distance, the so-called temporal coordinates. So in terms of these temporal coordinates, if the nonlinearity is weak, one can, of course, couple a localized pulse into the fiber, but it will start to spread out under the action of the dispersion. On the other hand, when the power of this input was made sufficiently large, what they observed in this picture, they observed the self-trapping of the optical power into this very narrow and very stable propagating pulse. And this was exactly the optical soliton. And moreover, this elementary solitons that we are talking about, it's, as I said already a couple of times, an elementary solution which everyone can easily find. what was a much more non-trivial result discovered due to the work by Zakharov and Shabbat is that this integrable equation gives rise to exact solutions in a much more sophisticated and completely non-obvious forms. For example, one can take this elementary soliton, multiply it initially by an arbitrary integer parameter n, and then one will, for each integer n, one will produce a new exact analytical solution, is a so-called high-order soliton of order n. So the fundamental soliton was n is equal to 1. This is the elementary solution that we saw. If we take n equal to 3 and so on, we will obtain the solution which will actually be localized, but it will not be stationary. It will demonstrate periodic oscillations. Because of these periodic oscillations, as if this is an object which is breathing. So the common name for such periodically oscillating solitons of higher orders is a breather. And in this very first experimental report about the observation of optical solitons and fibers, these authors were already able to observe at least the second order breather. So they took the power still higher than here, roughly speaking. Roughly speaking, by a factor of 4, because if you multiply the input by 2, the peak power will be multiplied by the square of this factor, by 4. And so this some observed picture of this higher order soliton is shown here, but it's not exactly the physical shape of the soliton. It is this central peak is an artifact which is not a real property of the soliton. It's simply an artifact produced by the experimental technique which was used to observe this object. What are real features are two side peaks, and they demonstrate that this may be a double-peaked object, so it may be breather or higher order soliton. Okay, next, another very famous experimental realization of solitons, effectively one-dimensional solitons, which are governed by essentially the same nonlinear Schrödinger equation. So this observation was reported much later in year 2002. I mean much later than solitons and fibers were discovered experimentally 22 years later, actually. After this explosion of works on the Bose-Einstein condensates in ultra-cold atomic gases, it was quickly understood that actually if this Bose-Einstein condensate ultra-cold gas is loaded into a quasi-one-dimensional trap, the so-called Seeger-shaped trap, it will be effectively modeled by the equation, which, as a matter of fact, is the same as a nonlinear Schrödinger equation. Actually, in that case, in the application to the Bose-Einstein condensates, usually this equation has a different name. It's called Gross-Pitayevsky equation because it was theoretically derived very long ago, approximately 1961, by these two people, Gross and Pitayevsky. And it was derived by them also for ultra-cold matter, but for a different ultra-cold matter, for liquid helium. And for the liquid helium, that nonlinear Schrödinger equation, it was derived if this, in that case, function psi is essentially the single particle wave function for this gas, which contains a huge number of particles. So for liquid helium, this model is very inaccurate for an obvious reason, because liquid helium is a state of matter with large density. However, for experiments which produced the observation of Bose-Einstein condensates, they always produce this observation in dilute gases. Actually, the density of experimentally observed atomic Bose-Einstein condensates is smaller, for example, than the density of air, roughly speaking, by 5 orders of magnitude. So it's an extremely rarefied gas. In that case, when it's extremely rarefied, this nonlinear Schrödinger equation, or in what is called the Gross-Pitayevsky equation, turns out to be an almost exact model, which effectively governs by the dynamics of this gas, and it demonstrates the dynamics of the gas in a very simple way. Instead of trying to, in the real experiment, usually this condensate is a gas in which the number of atoms in the real experiment is between 1,000 and 1 million, roughly speaking. And instead of trying to monitor the motion of each atom, it's enough to, in the so-called mean field approximation, describe all these atoms simultaneously by a single particle wave function. And then actually nonlinearity appears because the only essential difference of this many-body system, just from the single quantum particle, is that when we have a many-body system, sometimes particles collide. So in this mean field approximation, which is valid for the rarefied gas, when the collisions, roughly speaking, occur relatively seldom, not very frequently, in that case, it was demonstrated by Gross and Pitayevsky that the effect of collision will simply be represented by this effective cubic term, which should be added to the traditional quantum mechanical Schrödinger equation for the single particle. This way, one is essentially rederives the nonlinear Schrödinger equation. Okay, because the equation is essentially the same as the nonlinear Schrödinger equation in any case, it may predict solitons. And for the first time, these solitons were experimentally observed simultaneously in these two works. One was published by the group of Professor Randy Hewlett at the Rice University in Houston, and the other by the group of Professor Salomon in Paris, in France. So they ran the experiment in exactly the same atomic species. They used exactly the same species of atoms. It was lithium-7. Why lithium-7? Because for lithium-7, one can actually very accurately adjust the, roughly speaking, the intensity of collisions by means of some special physical effect. And then it becomes very convenient to use exactly this gas of lithium-7 to create states with where the strength of the nonlinearity may be adjusted to any desirable level. And to illustrate this, we can look at this picture. This is a famous picture. This picture is an image taken in the experiment performed by the group of Randy Hewlett. So what they observed here in this snapshot, they observed a cluster of more or less, you can count 7 solitons with very different amplitudes, different heights. But nevertheless, these are well-separated peaks. Each peak is indeed maybe quite reliably identified as an individual soliton. Of course, they interact, these solitons. Okay, now, a rather natural question is, okay, so we know that in the realm of one-dimensional physics, roughly speaking, we have very well-defined models, arguably the most important one is the nonlinear Schrödinger equation, but there are also some other very famous and very important equations. I mentioned already the Korteweg-de Vries equation, or another famous equation, which also has very important physical applications. It is a Sine-Gordon equation. In particular, it's a fundamental model in superconductivity for what is called the Josephson junction. Okay, so there are several fundamentally important and ubiquitous one-dimensional equations, ubiquitous because they're universal equations which appear in essentially the same form as models of completely different physical systems. For example, as I mentioned already, in fiber optics and in Bose-Einstein condensates. And also the same nonlinear Schrodinger equation has a large number of other physical realizations. For example, it is approximately a fundamental equation which governs the propagation of the Langmuir waves in plasmas. And also this is equation which simultaneously governs the propagation of water waves in the case, in the limit of a very, very deep water, the surface waves on water. Okay, and so then these equations easily predict soliton solutions, and it was relatively easy to experimentally observe these soliton solutions. Why it was relatively easy to observe these solitons? Because the mathematical analysis of these solutions demonstrates that they are stable. For example, we were talking about the elementary solution for the soliton solution for the nonlinear Schrodinger equation. As I mentioned, it's actually not a single solution, it's a family with two parameters, amplitude and width, and the entire family is completely stable. It's first of all the mathematical fact, and then it was very clearly observed in the experiment, because people were able to observe solitons with very different amplitudes and different velocities, and everything was stable. Now, if then the natural question is, what about the multidimensional situation? Of course, the real world is multidimensional, and then in many cases, actually, one may be interested to look at 2- and 3-dimensional equations, which in many cases can be, formally speaking, straightforward extensions of their one-dimensional counterparts. For example, one can take the nonlinear Schrodinger equation and write it not in the one-dimensional form, but in 2- or 3-dimensional forms. We will see it soon, how it's written. And then, for example, this for the description of the Bose-Einstein condensate, which is not reduced effectively to the one-dimensional situation by means of loading this condensate into the strongly elongated Seeger-shaped trap, but one can, why not to consider just a really 3-dimensional condensate, right? Of course, in many experiments, people were doing it with a completely 3-dimensional geometry. And then actually, this Gross-Petaevsky equation will be exactly the 3-dimensional extension of the one-dimensional nonlinear Schrodinger equation. Okay, therefore, if there are natural models in 2 or 3 dimensions, what about their ability to create solitons? Formally, it's quite easy to create such solitons. Actually, what should be stressed, of course, as I said, that an extremely important property of the one-dimensional nonlinear Schrodinger equation is its integrability, discovered by Zakharov and Shabbat. The 2- and 3-dimensional extensions of the nonlinear Schrodinger equation are not integrable. By itself, it's not actually a big disaster because of course, because of the lack of the integrability, one cannot find exact soliton solutions, but it's quite easy to produce them numerically. And also in an approximate analytical form, they can also be found by means of the method which is called the variational approximation. So this is sort of a technical problem, the lack of integrability. A really physically significant problem is something different. Unlike their one-dimensional siblings, these 2- and 3-dimensional solitons are usually subject to strong instability. So for them, stability is a very big issue and a very non-trivial problem, unlike one-dimensional solitons where stability is almost trivial in a sense. Why the stability becomes such a big deal for the multidimensional solitons? If we take this 2- and 3-dimensional soliton, actually, formally speaking, it indeed produces solitons. If we take 2- and 3-dimensional nonlinear Schrodinger equations, they will formally produce two and three-dimensional solitons, it's easy to find such solutions numerically. However, exactly the same equation produced in 2 and 3 dimensions produces a completely new phenomenon which did not occur in 1 dimension. This phenomenon is called collapse. A collapse means that one can launch a localized initial condition, and in the 2 or 3-dimensional geometry, the evolution of this initial input will lead to formation of a true singularity. So, of course, it's in the physical world, the true singularity will not appear. It will mean that the amplitude of this evolving object will become extremely high. Mathematically, it would eventually become infinitely large. Physically, of course, it cannot become infinitely large, but it means that simply the validity of this model will be violated. For example, in optics, the trend to the onset of the collapse will actually produce very strong values of the electromagnetic field, for example, and completely new physics will come into the play, such as, for example, ionization of the medium. But in any case, this propensity of the 2 and 3-dimensional equations to give rise to the collapse, to the formation of the singularity, is also frequently called catastrophic self-compression. Catastrophic, it means that which it is going to produce a singularity. So this immediately implies the instability of solitons, because soliton is also a localized object, right? We may have a mathematical solution for the soliton, but if you add a small perturbation, this perturbation may very easily provoke the may initiate the growth of this collapse. And then, unlike their one-dimensional counterparts, the 2 and 3-dimensional solitons will immediately become unstable, and this gives rise to a question if we can somehow change the underlying physics and introduce some models which will be still physically relevant in multi-dimensional geometries, but will be able to produce stable solitons. It's a really challenging problem, generally speaking. Okay, so to be more to talk in a more well-defined form, we can look at this 2-dimensional nonlinear Schrödinger equation. So if we compare it with the 1-dimensional equation, you see that formally speaking, it's really very similar. In 1 dimension, we would only have these terms u sub xx and would not have the second derivative with respect to y, to the second coordinate. Now we have 2 coordinates, and we have therefore 2 second derivatives. And then, formally speaking, one can easily find numerically soliton solutions. So a soliton solution can be looked for stationary solution in this form. It's conveniently written in the polar coordinates r and theta instead of the Cartesian coordinates x and y. So what is implied here? First of all, there is obvious dependence on time. So this parameter mu, in the case of Bose-Einstein condensate, is called the chemical potential. So in optics, minus mu would be called the propagation constant. Then S is an integer. Why we write the integer? Because obviously, if we write the 2-dimensional solution, we may have the fundamental soliton when this term is absent. But if we want, we can add this term to the phase of this soliton that we would like to find. Obviously, this term is possible if S is integer. And then we will actually, this object will become a topological object, because this S, it is a topological charge of this object, and this object will become a vortex. Or because we're talking about the soliton, it's a vortex soliton, or solitary vortex, whatever you prefer to call it. So then, mathematically speaking, if we substitute what's called this ansatz, so it's enough to assume that this amplitude function u, capital U, is simply real. And for this real function, we will easily reduce this equation to this ordinary differential equation with respect to the radial coordinate. Of course, one cannot solve it analytically, but it's quite easy to solve it numerically and find a whole family of solitons. Why family? Because for any negative value of mu, this equation gives rise to a well-defined soliton solution. So this is, for example, the two-dimensional picture which shows the distribution of the local squared amplitude in the fundamental two-dimensional soliton fundamental when the vorticity is equal to 0. So this soliton has a special name. It's called the town soliton. The reason is that it was first theoretically predicted in 1964 by 3 people, and the last in this team, it was a very famous optical physicist, Charles Towns. Therefore, it's now very common to call this soliton town soliton. Actually, in 1964, when they published this work, the word soliton did not exist. It was coined exactly the next year, in 1965, by Kraskal and Zabusky. Kraskal is, I already mentioned his name today, in the connection to the Korteweg-de Vries equation. In 1964, Towns and his co-authors, they called it self-trapped beam of light because they wanted to construct this object in optics. So this town soliton is the first soliton which was ever predicted in optics, but it has never been observed, unlike many other solitons. And the reason that it has never been observed is exactly the one which I already mentioned, that it is unstable. Okay, so now an essential property of this soliton. So as I mentioned also, this is not a single soliton, it's a family. Family because once again, we may have an individual solution for any negative value of mu. So we have a family of such solutions. And then it's very easy to prove, it's an elementary fact, that if we have this family of two-dimensional solitons is degenerate. Degenerate in the sense that all solitons with any value of the chemical potential have exactly the same single value of the norm. Norm, this is natural definition, the integral of the local square of the solution. Or in optics, for example, it will be the total, the integral power of the optical beam, or in Bose-Einstein condensate, is simply proportional to the total number of atoms in the condensate. So we have the family of solitons and degenerate because all the norms take the single value. The single value itself cannot be found analytically, but its value is very well known from the numerical solutions. And then actually one can take this soliton with embedded vorticity S, not only fundamental soliton, and then it's easy to prove that also for any fixed value of the vorticity, starting from 1, we have the family of such vortex solitons, and they all have exactly the same value of the norm. Of course, the norm depends on this fixed vorticity. In particular, there is a simple analytical, approximate analytical formula, which starting from S equal to 1 gives a rather accurate approximation for this dependence. And now, how collapse happens if we want to try working with the town soliton, with the fundamental soliton. So what is shown here is the result of the direct simulation of the evolution of this soliton when we have the soliton plus an extremely small perturbation. Actually, the perturbation was not even introduced. It's simply the perturbation which is inevitably generated by the so-called truncation errors, by the numerical noise, roughly speaking. So what is shown here is the evolution in time of the radial cross-section of this soliton. It's simply of its radial structure. So what we can immediately observe is the fact that originally soliton seems to be almost stable, but nevertheless, very slowly, the perturbation starts to grow, and then it accelerates, and eventually, after a finite evolution time, is going to create a singularity, an infinitely large amplitude here. So this means the town soliton is unstable. It's not a it's a beautiful solution, but it's not a physically relevant one. And then if we look at the vortex solitons with vorticity, they are still more fragile, still more unstable, because they're also stable against all sorts of the collapse, but they're still more unstable against the effect of the spontaneous splitting. So if we look at the top view of this soliton, so naturally it will have a hole in the middle because the vorticity actually drills this hole. It's like the fact that the Bessel function must vanish at the central point. It's the same fact. So this is what is called the vortex ring in terms of the top view. And this vortex ring is, first of all, very strongly unstable against spontaneous perturbations, small perturbations, which actually introduce this azimuthal perturbation and which break its axial symmetry. So due to this instability, this vortex ring will spontaneously split in a set of two fragments. Each of them will be more or less a fundamental town soliton, and it will be much later killed by the internal collapse. Or this is a similar investigation of the instability of the vortex soliton with embedded vorticity 2, double soliton. In that case, this is also a vortex ring, naturally with a larger diameter and larger size of the internal hole, which is drilled, which is made by the vorticity. And in this case, this object is most vulnerable to the spontaneous splitting into a set of 4 fragments, each will again be approximately fundamental soliton. So everything is terribly unstable, and therefore the problem is if we can produce something more physically relevant. Then we can recall once again the properties that if we look at, for example, the family of town solitons, we have the continuous family, all of them have a single value of the norm. And actually what happens is that in terms of the dynamical systems, we can say that we have 2 different types of solutions of the nonlinear Schrödinger equation. If we have a solution with the norm, input with the norm, which is slightly smaller than this single value of the norm of the soliton, it will start this soliton, this input, whose norm is slightly smaller, will start to spread out, to decay. On the other hand, if we take the norm, which is slightly larger than the single value, it will start to blow up. It will demonstrate the collapse. And therefore, the town soliton is what is called in mathematics a separatrix. It's a very special solution, which is exactly a boundary, which separates 2 different types of behavior. It separates solutions which spontaneously decay and solutions which spontaneously blow up. And of course, any separatrix by itself is always an unstable solution, because if you take a separatrix and add a very small perturbation, you will push its evolution in either direction, either towards the spontaneous decay or towards the blow up. So this, for the 2-dimensional town soliton, its single value of the norm plays a critical role. Is a critical value of the norm which separates different types of behavior. And for this reason, this collapse is called the critical collapse, because it really happens when the norm exceeds this critical value. In 3 dimensions, we also have collapse, but this collapse in 3 dimensions is supercritical. A supercritical means that the critical value is equal to 0. What it means that even if we have the input with an arbitrarily small norm, it will be able to initiate the development of the collapse in 3 dimensions. So the situation is still more vulnerable to instability in 3 dimensions than in 2 dimensions. And again, therefore, it's more challenging. Okay, and as I said, this is a problem. The most essential problem for the study, first of all, for the theoretical studies and then for attempts of experimental realizations of multidimensional solitons, is their stability. This is a dramatic difference from the 1-dimensional situation. And so this problem has recently drawn much interest, and there are in particular some review papers. This is, for example, this is a relatively short and relatively recent review paper on this topic. Then there is another review paper which specifically focused on multidimensional solitons with embedded vorticity and vortex solitons. Also, there is another review which is specifically focused on a completely different class of models, but also which also produce multidimensional solitons, but these are solitons in dissipative models, when we have not only the balance between self-attraction and self-spreading, but also the balance simultaneously between gain and loss in the dissipative medium. And eventually there is a book which was published approximately a year ago, and actually this book summarizes theoretical and experimental results which have been accumulated in these studies. Okay, and this is well, one more review paper which will appear very soon. Actually, it summarizes the recent situation in these studies. Okay, so because stability is a critically important problem for multidimensional solitons, the further presentation may be quite naturally organized according to different possibilities, which were first of all theoretically proposed, and in some cases experimentally realized, in order to somehow suppress the instability and produce stable 2- and 3-dimensional solitons. So the most essential possibilities for this are, first of all, we will consider a rather old idea. The idea is actually very simple. The idea is that we know that actually the instability is driven by the in the nonlinear Schrödinger equation by the cubic term with property of the self-focusing. In many physically relevant situations, for example, in nonlinear optics, it may happen there are optical materials in which nonlinearity is more complex. When the power is not very high, it is indeed the cubic self-focusing, but when the power becomes still larger, and we maybe have the gradual transition to the development of the collapse, the nonlinearity becomes different. So another physics comes into the play, and as a result of this additional physics, we can observe what is called the saturation of this self-focusing. So mathematically speaking, it means that we should add the additional still monolinear term, quintic term, fifth-order term, with opposite sign, self-defocusing. And so if we have the cubic self-focusing and then quintic self-defocusing, obviously collapse will be always arrested, because when the amplitude is going to become very large, the dominant nonlinearity will be self-defocusing. It will not allow the onset of the collapse. And therefore, it is a very natural idea is that the saturation of the cubic self-focusing may probably, it's obvious that it suppresses the collapse, and if it suppresses the collapse, it may have a good chance to stabilize solitons. So we will discuss it. This is a rather old idea. Then a relatively more recent possibility, which thus far was considered only theoretically without an experiment, this is an idea to stabilize 2- and 3-dimensional solitons in Bose-Einstein condensates by means of a specific effect, which we will discuss a little bit later, maybe not today, but there's a next talk next week. This idea is, this new physical feature is what is called spin-orbit coupling. So we will see what it means. It means that spin-orbit coupling by itself is a purely linear effect, but it's rather specific, but purely linear. And it is observed, it takes place in the 2-component condensate. It's necessary to have a system of 2 equations for 2 wave functions of 2 components. And then the nonlinearity may be kept just in the purely cubic self-focusing form, as the nonlinearity which leads normally to the collapse. And we will see that the interplay of this usual cubic self-focusing and this additional linear property, which is called the spin-orbit coupling, their interplay actually leads to the creation of completely stable solitons and suppression of the collapse eventually. And then hopefully we will have possibility at least to briefly discuss the most sophisticated addition to these results, which was not only predicted theoretically, but quite surprisingly, very quickly realized experimentally. It's also some effect which can be observed in a two-component Bose-Einstein condensate, but with completely different physics. This physics is actually, it refers to the fact that as I mentioned already, that the Gross-Petaevsky equation, or the same as nonlinear Schrödinger equation, it's actually essentially the semi-classical equation, which is derived in the mean field approximation. So, of course, it's an equation for the quantum state of matter, but the equation itself is semi-classical. And the possibility is to consider the effect of average effect of small quantum fluctuations around this semi-classical mean field state. So at the fundamental level, this was done very long ago in 1957 by three people, Li, Huang, and Yang. And Li and Yang are very famous physicists who received the Nobel Prize for the prediction of parity non-conservation in weak interactions. This is another very famous theoretical work by the same people. And what they did, they theoretically derived the additional nonlinearity, roughly speaking, which is a correction to the usual nonlinearity, which accounts for which is produced by the mean field or semi-classical approximation. And what will happen, we will see that in addition to this cubic self-focusing, the Li-Huang-Yang effect produces automatically correction. This correction is a high order term, not cubic, but quartic, fourth order term. And this fourth order term always is self-defocusing automatically. And then it will naturally suppress the onset of the collapse, and this it can lead to the creation of stable soliton-like objects, the so-called quantum droplets. And indeed, as I said, very surprisingly, very quickly after this possibility was predicted by Russian physicist Dmitry Petrov, who a Russian physicist who actually is a professor in Paris. So just 3 years after this prediction, such quantum droplets were already created experimentally, at least by two different groups. Okay, so this is a scheme of what we are going to discuss now. Today we have a few minutes. There was some delay because of the technical problems. If you agree, maybe we will extend this talk by 5 minutes to compensate this initial loss of time. And then let us start to discuss the first possibility. So the very straightforward idea is, okay, if we're unhappy about the onset of the collapse, let us add the higher order quintic term with the opposite nonlinearity, which will stop the collapse, will not allow it to develop. And then we will have to look at this equation, which is the standard name is the cubic quintic nonlinear Schrödinger equation. It's written in the three-dimensional form. The evolutional variable here is not time, it's z, because this is how this equation is derived in nonlinear optics. In nonlinear optics, the evolution is observed not in time, but along the propagation distance. And tau is actually the temporal variable, which plays the role of the third coordinate. Okay, then we have this cubic term that we already discussed several times today, and now this is its saturation, higher order quintic term with the opposite sign, with the self-defocusing sign. Okay, so then if we want to look for solitons, a very natural answer is written here, so we can assume that, first of all, dependence on z is obvious. We just have this phase k times z. K is called the propagation constant, or wave number if you want. and nothing else. And then we can we write this we instead of Cartesian coordinates, we use once again the polar coordinates r in the two-dimensional plane x, y, and theta. And then once again, we can, if we want, we can introduce the vorticity exactly in the same way as we already discussed it today. Okay, then what will formally, mathematically speaking, what one should do, one should pick up the ansatz, substitute into the equation, and immediately arrive at the necessity to numerically solve the stationary partial differential equation. Partial because now it's, you should find this real functions, u may be, capital U may be assumed real, but then it's will be a function of two independent variables, of the radial coordinate r and also of the temporal coordinate tau. And so this is a three-dimensional cubic quintic equation. Two-dimensional is obtained in the obvious way. We just drop this temporal term. In optics, it means that we consider the propagation of light in what is called in the spatial domain, when in the effective equation we have only coordinates and no time. Okay, and then first of all, what was done in two dimensions? In two dimensions, so the fact that fundamental soliton without any vorticity will be stabilized is obvious without any calculation, because of course the collapse eventually cannot develop if the highest nonlinear term is self-defocusing. So this is as a matter of fact a trivial prediction. What is very non-trivial is a possibility to consider the stabilization of the two-dimensional soliton with embedded vorticity. As I mentioned, in the framework of the cubic equation, the vortex solitons are the vortex rings are terribly unstable, not because of the collapse, but because of spontaneous azimuthal instability, which splits this vortex ring into a few fragments. And if we just add the high order quintic term, it's not obvious in advance at all if it may have any chance to stabilize vortex solitons against the splitting instability. So for the first time, it was sort of empirically found. Empirically, I mean by means of the direct numerical experiment by two people in Spain, Quiroga Tejero and Michinel. And so they just simulated directly the evolution of such a vortex soliton, and the fact that they found was originally a big surprise. The surprise was that if this is a fat soliton, fat means that it is a large soliton with a small hole in the middle. This small hole in the middle, this is a result of the vorticity. So the total size of the soliton is much larger than the size of its internal hole, but the hole, of course, must exist, because we have the vorticity. And in that case, when it's fat enough, sufficiently large, is the direct numerical result of this experiment was that they are stable against small perturbations. They are unstable if the radius of the soliton is not sufficiently large. If it's comparable, roughly, not much larger than the radius of the internal hole, then it's indeed splits. However, above some, roughly speaking, critical value of the radius, it becomes stable. And not only stable, but as you can see in this simulation, it's possible even to simulate collisions between such solitons, and they indeed behave as solitons, because solitons are objects which, when they collide elastically. They do not destroy each other. They either pass through each other or they bounce back. So these guys, they bounce back when they collide. So because they start to collide, this is a minimum distance between them, then they start again to separate. They bounce back, and they bounce back quasi-elastically. They slightly deform each other, but do not destroy each other. So this is a quasi-elastic collision. It's quite a surprising result, as a matter of fact. And then what about the possibility to observe this fact experimentally? First of all, the stability of the fundamental soliton without any vorticity in optics in the case of this nonlinearity was demonstrated in this work. But as I said, in terms of the theory, the result is completely obvious. Of course, it was important that it could be exactly demonstrated experimentally, but it was obvious that it did this, nothing else, but only this stabilization could be observed. However, as I mentioned, what is very non-trivial is the prediction of Quiroga, Teixeira, and Michinel that at least some of the solitons with embedded vorticity can be stabilized as well, and the same mathematical problem was analyzed in a much more rigorous form in this later paper by Pego and Warchel, and they just demonstrated that indeed, in a more accurate form, a part of the family of vortex solitons are stable. For example, this is a set of radial profiles of such solitons with different values of the topological charge. So, for example, this is the soliton. This one is a soliton with charge 1. This soliton with a much larger hole with charge 2. With this is its peak, charge 3, charge 4, charge 5, and so on. And each soliton with any, in principle, the soliton with any value of the topological charge may become stable when its size becomes sufficiently large. What is shown exactly here in this plot, this is a set of such profiles. Each one is taken exactly at the boundary between unstable and stable vortex solitons. So if the size is larger, they become stable. If the size is smaller, they are unstable against splitting. And the last thing maybe to be mentioned today is that, okay, what about the possibility to observe this non-trivial results, the stabilization of vortex solitons is the experiment. Thus far, there was, as far as I know, there was no direct and straightforward demonstration of this prediction. However, in a partial form, it was demonstrated, particularly in this experimental work, and it was demonstrated in optics. So the optical soliton was created in this cubic quintic medium. First, in the left column, what you can see is this is a case when from the very beginning the input is quasi-linear, its power is small, and therefore it just demonstrates, or it's created with the vorticity. It's not a big deal to create it with the vorticity. And then this vortex ring, it simply starts to spread out under the action of the linear diffraction. It's a purely linear evolution. However, this is the situation which was observed experimentally when the power was sufficiently large. In that case, there was a trend to form a soliton from here up to this stage. So the soliton was able to support its structure over the propagation distance, which is 5 times what is called the Rayleigh length. So Rayleigh length is a characteristic length necessary for the demonstration of the diffraction effects. So there was a trend to produce such a quasi-stable vortex solitons, but eventually the point is that in this material medium where the experiment was performed, there is a dissipative effect, the two-photon absorption. So some nonlinear dissipation. This nonlinear dissipation starts to gradually eat the power of the soliton, and therefore, because of the loss of the power, it eventually switches from this nonlinear regime into the same linear regimes that we observed here. And then this object ceases to be a soliton and starts again the rather trivial process of quasi-linear expansion under the action of the diffraction. So this is the only result where partial stabilization of the two-dimensional soliton with embedded vorticity, vorticity 1, was somehow observed. Okay, so I guess that today we should probably stop. Okay, really the very last thing to mention today, just to be done with this simplest topic. We discussed stability and stability of these solitons in the cubic quintic equation in 2 dimensions. Finally, what about 3 dimensions? In 3 dimensions, once again, the stability of the fundamental soliton is a trivial fact, as a matter of fact. What is very non-trivial, one can construct a stationary solution in the form of the vortex torus, or what people call donut, such an object. This is a three-dimensional soliton with embedded vorticity, with vorticity 1. And here the prediction, the numerical prediction, was that in this equation there is some region of parameters in which such a three-dimensional object, this vortex donut or vortex torus, will be stable if its vorticity is exactly equal to 1. And this is the demonstration of this prediction. One can construct such a donut and then add a relatively strong random perturbation, and it quickly restores its unperturbed shape because it's a stable object. However, all these three-dimensional solitons, donuts, with a topological charge higher than 1, 2, 3, and so on, they are completely unstable. So this is an example, spontaneous splitting of this three-dimensional donut, this time with vorticity 2, and it's almost unstable. In this case, it prefers to spontaneously split into a set of 3 fragments. Each fragment is a stable fundamental soliton. Okay, so today it's really, I guess, a good point where we should stop. And so let me just mention that what will be the initial point in the next talk. It will be something which already is not so much, such an elementary tutorial, but rather a report of some more relatively recent research results. And this will be, first of all, which I've in 2 words already mentioned today, the very non-trivial prediction of the stabilization of 2-dimensional solitons with some, as a matter of fact, with some vortical structure, due to the purely linear effect, which is called spin-orbit coupling, and which is a very popular topic for studies in Bose-Einstein condensates. Okay, so here I should stop for today. Arigato, and thank you very much for your interest.